Okay, should I start?
Yes.
Okay, thank you. First of all, I wish to thank Zoe for all the efforts she has made in the past years to create ALLODD. This is her own creation and the very successful results which have been obtained at the European level. And at this stage, I think once again, she has been the main actor, and I wish she'd be recognized for that. But perhaps next year and others, the ALLODD will be continued. And again, this is due to her. So thank you for inviting me for this lecture, and I wish to say that several of you may have heard me already in the past, but it's not working. Okay, Zoe asked me to give some historical aspects in this 45 1-hour lecture, so that all the students who are there will have heard about Allostery from one of his initiators. So the beginning will be something that most of you know, but I will repeat it. And then I will move to some more elaborate results on concept about the allosteric transition. And there I will mention, of course, the work of Marco, who is here and has been a pioneer in it. And the second part, or last part of my presentation, is to look for the future of allostery and to see to what extent one can link the molecular biology of receptors to higher brain function, and even to have a new psychopharmacology. So let's look first to the fundamentals. The concept originates from the thesis work I did on threonine deaminase, which is a bacterial enzyme, which was discovered by Edwin Umbarger it was shown to be the first enzyme on the pathway to agency, and feedback inhibited by the end product, isoleucine. And in addition, he discovered there were also some threshold in this effect and what we call now cooperative effects. So one of the first experiment I tried to do in pharmaceutics is that I had the hypothesis in mind that there was a selective mechanism involved in this feedback inhibition. So if there was some, one should be able to dissociate the feedback inhibition from the activity of the enzyme. And that's one of the early experiments I did, where using heating, which is a very crude way, I was able to show that if the enzyme at the beginning is inhibited by a solution, it loses inhibition without losing the activity of the enzyme. So that there was an uncoupling between the activity and the regulation of this activity by the feedback inhibitor. This was published in 1961 in the Curie Symposium of Quantitative Biology, and very interestingly, in parallel, Gerard and Tardif found similar results. So the model I proposed in this 61 meeting was that in addition to the classical model of steric inhibition, we call today orthosteric effects of the ligand, then there could be another mode which would be uncoupled by the treatment, where two sides are present, one for the substrate, the other for the feedback inhibitor, and the two would be linked. The interaction would be called allosteric and mediated by a conformational change. So this was the definition which was given in this 1961 symposium. Now, continuing on the observation of Barger and the work of Mercedes' work, and was able, and this was also found with others, that there are strong interrelationship between cooperative interaction and feedback regulation. And you can see here that, for instance, you may, during uncoupling, lose the cooperative interaction and even have an increase of affinity when the uncoupling takes place. So this was discovered in parallel with the work of different Wyman and hemoglobin and Pasteur, where they also found that these cooperative effects for oxygen value could be modified by ligand like proton and Bohr effects. And Max Perutz at that time was able to find the structure of elucidate the structure of oxyhemoglobin, and that was the first X-ray structure of an oligomeric protein made up of several subunits with one true dyad and two pseudo-dyad asymmetry. So the idea came out from us that the cooperative effect associated with the feedback regulation that we found was associated or determined by an oligomeric structure as the one found in hemoglobin. And this is exactly what we postulated in 1995 at the end of this work. I wanted to have some kind of theoretical conclusion, and this was done by Jacques Monod, if you remember myself, from the work I did on Mercedes and also work done by others. So the first proposal was that allosteric proteins are oligomers, that they may undergo spontaneously some conformation transition between two states, resting and active state or a tense and a relaxed state, and that the symmetry is conserved during this transition, and thus the transition involved the quaternary structure, the oligomeric structure, which is creating some constraints on the conformation transition. And last but not least, ligand stabilize some state, either the active state or the resting state, and therefore activator or inhibitor of the signal transition is mediated by this pre-existing conformation transition, which can be qualified by an isomerization constant L. And the equation will derived, and the outcome of this formulation was the distinction between two functions, a state function and a binding function. The state function, which qualifies the conformation equilibrium, which again can exist in the absence of ligand, and the binding function, which is the measurement of the actual binding to the overall system by the ligand. So this distinction is important, since it could be a criteria for us to test the model. So this is a minimal model of signal transition by selection of pre-existing conformation of cooperative oligomers. So this is, if I may say, some kind of Darwinian mechanism compared to an instructive induced fit mechanism of Kochland. So this model has been wonderfully illustrated by the work of Iwata and colleague on this bacterial lactate dehydrogenase, where he co-crystallized in the same crystal the resting and active conformation. And you can see here the beautiful symmetrical oligomeric structure of the molecule, the perfect conservation of symmetry, and in addition, a very important observation that the catalytic sites and the regulatory site are at interface between subunits, so that it's easier when the conformation change modify the quaternary organization to alter simultaneously the active and the regulatory site. So this work was demonstrating that the quaternary transition here, where the subunit does not change much, is in fact associated with the rotation of the subunit. So this is, of course, an observation which is beautifully consistent with the two-state model I showed before. Now, I demonstrated that by deriving the equation of the model, one could distinguish a state function for the conformation chain and the binding function for the actual binding of ligand to the root system. And when I was in Berkeley with John Gerhardt and Howard Sherman, I was able to demonstrate that indeed in this system, the state function, which was mostly identified by John Gerhardt and the binding function were critically distinct. So this is very evident, but preliminary, of course, on the first stage demonstration that the WC model is okay with aspartate transformamidase as opposed with Lucefran. So this is just a summary of the fundamentals of Allostery, as I said. And the question I raised already in my PhD thesis, which is quite a while ago, I will see here, was how general is the model can be extended to brain communication. So at that time, there was not a single receptor or neurotransmitter which was ever identified. And it was known from pharmacological experiments that at the synapse, where there is a neurotransmitter in the nerve ending released in the synaptic cleft, then the receptor is binding to neurotransmitter receptors. Now, the electrical response in the case of the neuromuscular function was known, but there are also other receptors where phosphorylation or other kind of response is observed. Here, in the neuromuscular synapse, is an opening on the channel. And I want to say from the start that there are hundreds of neuropeptides, at least 12 small molecule light acetylcholine, dopamine, or epinephrine serotonin, and maybe thousands of receptors for neurotransmitter present in the brain. So one may say that the brain is a highly diversified chemical machine. Now, I had to identify a receptor to really test the allosteric scheme on this receptor. And I went to David Nachmanson, who had been using the fish electric organ, and started to work with him, and then developed at Pasteur a method of isolation of the electric receptor from the electric organ, using a very specific label, which is a toxin for snake venom, which was given to me by Shane Wondry. So using both fragments of membrane from the electric organ from electrophoresis electric torpedo, from the electric organ and snake venom, one was able to identify and purify and have the first observation of the receptor by electron microscopy. And you can see already here by Jean Carteau from electrophoresis, as I mentioned, and torpedo. And you can see here the structure, first structure ever published of receptor which look like a beautiful pentamer. And indeed, this is a hetero-pentamer because it's the same receptor as the muscle receptor, 2 alpha, 1 beta, 1 gamma, 1 delta. And following that, first amino acid sequence was identified, and the full sequence, and a two-dimensional hypothetical model proposed with extra membrane synaptic domain, cytoplasmic domain, and in between 4 transmembrane domains, and one of them being the ion channel, by anticipation here, and then 2. So this was a 2D model which was proposed from the result obtained by Newbar, by ourselves. And this was, if I may say, the first neurotransmitter receptor identified as a protein. Now, is this an allosteric protein? And if you, after 40 years, even more research, the results from the review we published with Marco Secchini, Pierre Changeux, and myself, which is a high resolution extracted cytography plus high resolution electron microscopy of the nicotinic receptor. And you can already see the synaptic domain, the cytoplasmic domain, the transmembrane domain, with the receptor site for nicotine here in the extracellular domain, and the ion channel, which is lined by the M2 transmembrane sector in the transmembrane domain. So this clearly shows that the sites for acetylcholine and the ion channel are far distant, about 60 angstrom, and therefore we have here a relationship between active site and ion channel, which has to be mediated by a conformation chain, and therefore it's, if I may say, a bona fide allosteric protein. Now, this is, of course, a first step for drug design, which should be done now more easily, knowing the actual structure of the receptor site, and therefore design drugs at the level of the atomic structure of the binding site. Now, this is from the nicotinic receptor, and meanwhile, Pierre Changeux, a colleague at Pasteur, was able to identify GLIT from bacteria as showing a receptor which was initially identified from a sequence point of view, but Pierre Changeux was able to obtain an active functional aggregated ion channel, as well as infant that's rare. This has a high resolution, little bit later, but much better resolution, and therefore continue at the beginning of the 3D structure of the receptor, of the GABA receptor by Higgs and Duo, glycine, serotonin, nicotinic receptor, alpha-4 and last but not least from the torpedo electric organ, and therefore we are closing the loop from the electric organ and alpha-toxin up to the structure of the receptor. So this is a very interesting observation, which already from what we want to show today is the basis of the extension of the idea of the allosteric receptor obtained with the electric organ now to the brain, and therefore that the actual bacterial origin of our brain receptor will be imposing some kind of constraint bottom-up on the way our receptor function, and we'll further discuss that later on. So this is now what I wanted to say. And these early findings were also enriched by another extension of the allosteric scheme to modulators of this receptor. And it was found that, for instance, with the GABA receptor, benzodiazepine, very early acts as positive allosteric modulator. In our case, we work with ivermectin, with calcium ions, and other compounds. And these modulators do modify the allosteric equilibrium in many from open-end flows, and we'll come back to the desensitization in a few minutes. And the importance of these sites is that they are not orthosteric sites for the neurotransmitter or the enzyme, but they bind to sites which are outside the orthosteric site. So here on the synaptic domain, here also in the transmembrane domain and in the cytoplasmic domain as well. So we are dealing with another category of regulatory sites, which we call modulatory sites, which are distinct from the allosteric site, and which are important because there is less interference with the neurotransmitter when one wants to design drugs which regulate and modulate these receptors. So it's a new strategy for drug design. Just to illustrate the case of ivermectin, the work that we did with Daniel Bertrand. Here is the effect, the activity of the alpha-7 nicotinic receptor of ivermectin, more than 100 times potentiation of the response, and the consequence of this activation can be abolished by a mutation in the transmembrane domain, and indeed the site is within the transmembrane domain. Here you can see in yellow the ivermectin binding site in the transmembrane domain, which was identified by its below. So we are having allosteric modulatory sites, which are not only present in the synaptic domain, but in the transmembrane domain, which is again quite far distant from the active site and from the ion channel, which is in fact closely related to M2, which is so we have a new category of allosteric modulatory site. I just want to show here the last result obtained by Marco and team and Pierre Changeux. And you can see here on the glycine receptor that there are at least 6 different categories of allosteric sites, and there is a database for the sites published by Marco, and here same thing for the nicotinic receptor. And you can see that there are ligands, including tetrahydrocannabinol, on the glycine receptor. And here, another aspect that I will not mention this time, of nanobodies, which can act as allosteric modulator at the level of the extracellular domain, which has been recently by Pierre Changeux, introducing the importance, if I may say, of this new pharmacology of allosteric modulator. Now, I mentioned that sites which are topographically distinct have to interact in some way, and the way it is, you have to have conformation chains as postulated initially in the two-state model. Now, very early on, Thierry Edman in the laboratory using a fluorescent derivative of acetylcholine, as you can see here, was able to measure by stop flow several relaxation times of the membrane bound receptor and fast Biomedical flow and proposed that in addition to the two states that I already postulated for the MWC model. Then, in the case of the nicotinic receptor, there are at least two additional states, which is an intermediate state and a desensitized state, which are slowly accessible, while this close to open is a very fast, the millisecond state, while this is 100 milliseconds to second. Now, a very interesting observation was done by Jackson in already 1986, that there might be spontaneous opening without acetylcholine of the ion channel. So this is in favor of the pre-existing conformation between the resting athlete and with Curie and Mann. We were able to show that there is also the case for the desensitized state, which may be present in the condition which we have here between 10 and 20%. So it means again that all these states can be pre-existing to the binding of ligand, which is one of the key postulates of the two-state model. So it means that it's not anymore a two-state model, but a four-state model. And as we shall see, in fact, further discussing that we were done by Marco Ciccini or something like that. Now, I had only a few slides about the conformation change, which has been occupying us for many years. And first, the express structure of glyph, closed and open, where you can see here. And this was done by Pierre-Jean Changeux and by Curie. And the idea is that there is a twist taking place between the synaptic domain and the transmembrane domain, which was already postulated by Antoine Taline, by a different method. And this is, in fact, confirmed. The twist is confirmed, plus some kind of blooming, which is taking place. Now, using molecular dynamics, I'm sorry, the model is not working, but computer, but Marco, together with Martin Carpus and colleagues, and Antoine Taline, has applied the molecular dynamic simulation to the glycine glucine receptor, and that's also, of course, a challenge because there's a lot to understand in that term. So he was able to develop this two-state mechanism at atomic resolution, which is again consistent with the two-state model initially proposed in 1965. Now, the other interesting thing is that this was done with eukaryotic receptors from the words, but has also been found and measured with the alpha-7 nicotinic receptor. And therefore, this dynamic of the transition imposes constraints on brain receptors. And you may have wonder why our brain is so slow, is working at the speed of sound, while our computers are working at the speed of light. Why is it so slow? The hypothesis I want to formulate is that because we are having in our brain ancestors of bacterial receptors, which impose to us a slow dynamic, at least their own molecular dynamics of protein. Now, this allosteric transition for activation have been resolved essentially by a unique group. You can see here the data. And we propose with Marco that there are different steps in the allosteric transition from the orthosteric site being closed in the resting conformation. By acetylcholine, there is some kind of global tilting to transmit the signal, and then the outward translation, leaving the opening of the ion channel. So this is, of course, inspired by this own simulation method as a result of Curie. And therefore, what we call some kind of wave, a conformation wave from the synaptic domain to the transmembrane domain, which has been further documented by Jean-Pierre Changeux with a twist and bloom, as I just illustrated now. Recently, this is the very last paper in PNS by Marco, very graduate student who was in fact remunerated by the Human Brain Program, that Marco and colleagues were able to identify the structure of the and simulate the structure of the active resting and the sensitized, and follow the opening by computation of the ion channel, and show that in the desensitized conformation, compared to the active open, you can see here, for resting close to Angstrom, there are several states for the desensitized state. One which is closed, of course, which is the name, but other which is open, as you can see here. So it means that there are some active conformation which occurs in the desensitized state. Now, this is, of course, an interesting complexity of the system that you have definitely the resting, the active, but additional desensitized state, resting, closed and open, which fits with this related to propose experiment. Now, this is of interest for pharmacology, since, as you can see here, as I mentioned, ivermectin is an allosteric modulator. So it potentiates the response. You showed the slide with an emphasize of 100% activation of enhancement of activation by ivermectin. And here you can see indeed that there is a potential. But this is another way of illustrating the effects of ivermectin. And here it's neutralization with the alpha-7 nucleotide receptor. And this was done in collaboration with Gibbs from California. Now, the interesting situation is that in addition to ivermectin, there are other pharmacological ligands which are active on alpha-7, like PNU or T2S, and these have an other additional interesting effects on the desensitization. And you see that there is some step here, which is characteristic of these type 2 allosteric modulator, which also find actually location which are close to those of ivermectin, though not exactly the same. So the question is, how can we relate this type 1, which is potentiation, type 2, which is blocking transient rate of desensitization? It is important to understand the pharmacology of the compound. And from the EM structure, one can see that they are indeed with PAM1, like rather large channel, but close to the open conformation, and with type 2 open conformation, which is here, you can see it's 12 on 12. We go back, I don't know. Can I go back? No. I cannot go back. What should I do? Okay. So here, with PAM2, you can see that the channel is open. Right. time. Why this close? Here you can see that we find one. There is a mistake here. So we have an image where in the presence of PAM1, which is just giving the activation channel open, and we find 2 open, but in the desensitized conformation. So this means that we have a positive allosteric modulator like PAM1, which are active on the condition for which here, and other of second category, PAM2, which are stabilizing the open desensitized state. So to be clear, PAM1 activation, PAM2 blocking desensitization, and keeping the response active. And the proposal that is made by Marco is that here these compounds, PAM2, are stabilizing the desensitized open conformation. So this is an interesting consequence of the allosteric pharmacology I mentioned before, not only PAM and NAM, but subcategories of PAM 1 and 2, which one activate only the active state, and the other stabilize a new desensitized open conformation. So now I'm going to allosteric disease and how we discovered this allosteric disease together with Daniel Bertrand. So going back to these early times in the 90s, we wanted to test the finding we did by photoaffinity of the ion channel. And this photo labeling showed that these amino acids were labeled. So they were just parts of the ion channel. So that's for sure. It has been confirmed by Sackman and many others. So there is no problem that M2 line the ion channel. So we said, okay, we are going to mutate these amino acid and see what happens. It should block the ion channel. So we made the mutation like this L247T, and then I gave it to Daniel, who did the extraphysiological and Curie. Oh, I'm sorry, there is something extremely interesting that I clearly don't understand what's happening. Instead of having the channel blocked, the affinity of the receptor and the activity was increased by 100 times. So this was the discovery of the first constitutive mutation, which in fact, instead of having the ion channel block, gave it open permanently as a consequence of the mutation. So we had, in fact, found a new mode of mutation which altered the function of the receptor through sites which are nothing to do with the active site, but connects with the active site in an allosteric manner. So the idea we propose is that we stabilize high affinity open conformation. So this is, of course, origin from many diseases. There are tens or hundreds of diseases which are caused to the constitutive mutation of receptor, like, for example, the thiamine kinase and so on and so forth. So this is quite a discovery. And now, very interestingly, unfortunately, the video is not working. Bertovic in Australia was able to find, he was studying an autosomal dominant nocturnal frontal lobe epilepsy in the child, and he was able to identify the cause of the disease which is an autosomal mutation in the transmembrane domain TM2, where exactly at the place where we identify ourselves. It's so that was really a beautiful demonstration that the constitutive mutation that we discovered from a purely fundamental question to solve paradoxically the paradoxical finding could apply, in fact, to medicine and give some interesting interpretation of the disease as the stabilization of an active conformation of the receptor, which leaves a stable open channel conformation, which could be treated by some nicotinic antagonists, but also the treatment unrelated to the nicotinic receptor. So this is, of course, a disorder of consciousness, it's an epilepsy, where we can make a very first link between the receptor and the consciousness. Now, other mutations were found by other groups, which was myasthenia gravis, which is some kind of paralysis of the neuromuscular junction, which is hereditary. And here the analysis was extended, and again, inside found that in fact there are a mutation which give a positive gain of function in green, and in red, loss of function, not only in the transmembrane domain, but also even in the extracellular domain. So we have mutations which in fact alter the overall transition from the resting to active to desensitized states, without necessarily acting, of course, on the active site or the ion channel. So this is the further discovery and generalization of the effects we found at the beginning. And the question we posed was what is the reason why these mutations are altering the allosteric transitions of the nicotinic receptor. And this was the reason of the work with Antoine Tailly and both the late Martin Farcus at the meeting in Strasbourg, organized by Marco, in the seminary, which was a very good meeting. And just to be told that the conclusion of this finding is that the amino acid which give rise to the constitutive mutation are located at the interface between subunits. This emphasizes again the contribution of the quaternary organic backbone, which was already in the two-state model. Remember the change of the two states, and which is here illustrated and giving a demonstration of the contribution of these amino acids to the transition of the receptor. And to just further confirm this finding with a very recent work of Marco and his team with Ryan Leaves, is that indeed, when you look at the active conservation, which is being stabilized by the mutation, you find that the channel is open, and it is computationally a desensitized state. So it's exactly the active desensitive site conformation, which was demonstrated initially by the molecular dynamics. So we are situation where we can say that the mutation that we identified initially as L255 stabilize the desensitized state, which is open, and give the epileptic phenotype. So we link the mutation to the actual phenotype. So we are in position now to extend. I have 10 minutes to extend the model to higher brain function. We are already there, but we can further extend to see to what extent one can apply the model to higher brain function. So this is a general model that we just published recently. And early on, with Curie and Mann, already in 1982, we proposed, and here is the model, that in fact the transition between resting and desensitized, which is spontaneously taking place, but could also be regulated, in particular by other synapses, can control the efficacy of the synapse. And here is, if you wish, the simple-minded scheme that we propose, where even this receptor could receive, for instance, a reward signal, an activation signal, and acts as a coincidence detector. For those who are interested, you can look at the paper themselves. So this is, if you wish, a way to approach higher brain function by assuming that synaptic efficacy could be allosterically modulated through the regulation of desensitization. So can we show that? So as I said, we have to go from the molecular level of the allosteric production up to the conscious process and illustrated with epilepsy. Now we had a theory with Senator that we developed in 1998, which is quite a while ago, 20 years ago, which shows that in fact to have this high level integration from molecular to neuron to network of neuron, to how to link these networks of neurons at the whole brain. And the idea of the whole brain is that we have neuron which link one part of the brain to the other, here and there. So these were neurons with long range axon, with all of the demonstrated by Ramon Claral and by Leslie, and here illustrated by Patricia Goldman-Watkins to make this kind of network where the prefrontal cortex is a key center of this network. So this emphasizes the occurrence of this long range axon network and the importance of the frontal cortex in higher brain function. But where does allosteric to affect this global neuronal network? So we made a model with Stanislas, again, quite a long time ago, where we propose a minimal global neuronal workspace for a given cognitive task and cognitive task. So we propose that there are processors which are non-conscious, and there are input and output here of these processors, and internally some kind of global workspace which is regulated by the reward system. You are right or wrong, so you select or not select the end of the task. And the proposal we already made at the time that the reward was acting on the global neural space through a chemical PEP synapse, which is exactly what I mean. So there is at least a consistency between our views about higher brain function and the particular conscious processing, hypothetically, of course, and allosteric through the action of the reward on the global effect by changing the conformation of receptors through allosteric regulation. So how to test that? So we saw that in schizophrenia, there are failure in conscious processing, which can be illustrated by deficit in conscious conflict monitoring stars and deficit in conscious error monitoring stars. So these are cognitive stars which are used by Martineau and Ram to qualify the state of consciousness of schizophrenic patients. You can also see that control and patients, they are really the deficits of the prefrontal cortex, some hypofrontality, which is taking place. Therefore, the issue is how to relate this hypofrontality to allosteric modulation. And first of all, there is some case of schizophrenic patients which are under genetic control. So there have been plenty of human data which led to the interesting finding that there are some genetic predisposition to schizophrenia also in humans, which involves 3 genes from the nicotinic receptor, alpha-5 and alpha-4. Now, one can build models from the data from the alpha-5 and have some kind of SNP of the alpha-5 introduced in mouse and look for this so-called schizophrenic type. I'm sorry to say that. Not correct. Mouse cannot be schizophrenic, but a very primitive model of the mouse, which after mutation knockout of the alpha-5 has some deficit in self-administration and in social life. Here, we see the alpha-5 SNP out. So there is some kind of deficit not only in self-administration of nicotine and social life in this mouse. So how can we interpret these effects at the molecular level? Now, this is just, of course, an ongoing kind of experiment, but since I talk about the future of ALLODD, here you can see that one can find the alpha-5 receptor in the pyramidal neuron from layer 6 of the prefrontal cortex. So you can see here that with the SNP of alpha-5, then there is a deficit in the response to acetylcholine. In the case of the KO mice, the deficit is stronger. Now, the Maslows and Curie found a very interesting finding that this compound is already known as an inhibitor of acetylcholine is a PAM of alpha-7, alpha-5, sorry, nicotinic receptor. So here you see the result. There is a very significant reversal of the mutation by the PAM, and therefore some attempt to cure the phenotype of the disease. The effect of the SNP, stabilize the closed state. Here the effect of galantamine, which open allosterically the closed state. So there is a correction of the dysfunction in the rats, in the mouse. So galantamine is a model drug against a higher level brain disorder. And again, there is a link through the prefrontal cortex in the prefrontal neuron, which show deficit and cure, if you wish, the hypofrontality of the this is just to show that there are indeed drugs which are under clinical test, 2 PAMs at least. And last, I will conclude by saying that there are also muscarinic receptors, which are different from the nicotinic receptor in the sense that they control the G protein and therefore internal signaling. And recently, a new neuroleptic was found, which is an allosteric M-form agonist of the muscarinic receptor. And now there is on the way, and this for us a very happy finding, that there is a PAM of the M-form muscarinic receptor, which is under ongoing clinical aspect as a new anti-psychotic drug. So from allostery to cognition and pathology. These are additional examples of 91 allosteric modulators available in medicine in general, including those for anxiety, insomnia, bipolar disorder, and now schizophrenia. And the take-home message is that there is a validity of the concept of allosteric interaction of the two states, but there are more than two states. That's clear from the presentation. That there is an importance of allosteric mediation, that allosteric mediation of ultimate resolution can now be resolved, and the new pharmacology is going to be proposed. So, Marco, and some of his colleagues, Pierre Jean, and of course, HBV, and Zoe Cournia for her invitation, and hope that she will be successful in the future. Thank you very much.
Thank you, Pasteur. And we have dedicated some discussion. Are there any questions from the audience? So we will come here. So, do you think there are any upper limitations to the size of an allosteric modulator? Because the consortium have also been investigating allosteric antibodies. So do you think there's any upper size limitation to allosteric ligands?
I think there are new allosteric ligands to be found, new categories, and you mentioned the allosteric antibodies. I did not want to go too far there because it would have been an additional talk. But the work of Pierre Jean, you could invite him for that, is beautifully illustrate that some small fab, very small size, with tissues, can be positive allosteric modulator and negative allosteric modulator. So there is an open field now, and I may even say perhaps a new pharmacology, which would not be based on organic chemistry, but on antibodies. A new psychopharmacology based on monoclonal antibodies. This is the future.
Yeah.
So describing the gating mechanism, the cascade of effects that start from the neurotransmitter binding to the gating of the channel.
Can you repeat the question?
Yeah, of course.
No, I'm sorry, I don't hear you.
Okay. You saw a slide.
Sorry, can
you hear me?
Yeah, I hear you better.
Okay. You showed us a slide describing the gating mechanism.
Yes.
the cascade of effects from the binding of the neurotransmitter to the channel opening.
Yes, yes.
Does this mechanism apply in all subtypes of NAC charge? Given that there are differences in the sequences, and I suppose that the interaction of residues that lead to the channel gating are not so concerned.
I think you are asking about the conformational transition from a
Exactly,
gated
yes.
event at the atomic resolution. That's what you are asking.
Exactly, yeah. He showed us the movement of loop C, how.
I think this is what I try to illustrate in a slide, which is published actually in the annual review of biochemistry. You can find this list of description that which I took from Marco. And concerning the beautiful allosteric transition of a classical allosteric enzyme, you remember I showed one slide where clearly what's happening is a tilting of the subunits. The angle of rotation is by a few degrees, and this is enough to change the conformation of the whole molecule without much change of the tertiary structure. Very little change, mostly change of quaternary. I remember historically from the student who were there, I had the pleasure to have dinner with Max Perus, who was at the very early stage of the identification of the conformational change occurring in hemoglobin. And Max told me, oh, I found an interesting result. We have change of quaternary structure without change of the tertiary structure. So I said, this is not possible. I'm sorry to say, I cannot believe that. He said, yes, the data are there. So it means simply that the resolution was not good enough to show that there is indeed, of course, some critical tertiary change which actually link the heme together through the boundary of the subunit. So there is some linking here at the atomic level. But it's more discrete than the change of quaternary structure, which is present, and which is also present in our case. So I think you have several levels of resolution of the conformational change, and the main one is the quaternary change. I studied, and then if you progress, you can go not only the propagation of the wave, which is itself much more discrete with a twist and so on, and boom, at the atomic level. The question is, all receptors?
Not all, but this type of.
Of course. Well, this is we think it is common to all the ligand-gated ions. I think there is some evidence for that, because we go from the glucose receptor to the glycine receptor to the nicotinic receptor. So they clearly it's valid for ligand-gated ion channels. Now, for GPCR, the Kobilka group and others have shown conformation, but they are still forgotten the general principle that GPCR are oligomers. So from the beginning, for 30 years, they simply ignored the fact. But Bouvier and others in Canada have not followed the MAGA view that it is a monomer, but a more elaborate view that in fact they are actually oligomers of GPCR, which are in fact the active conformation.
So thank you for the very nice overview of many different aspects of the problem, historical, but not only historical. I was I had curiosity about the case of galantamine. Then maybe I don't know very much. So you have this effect of galantamine on the alpha-5 SNP, we call it. So it's a mutation. And you said that galantamine can correct for the mutation, effect by shifting the equilibrium to the active state. So I was wondering, do you need a positive allosteric modulator for this, or an agonist, an allosteric agonist will still work?
Now, I think I showed you the mutation of alpha-5, which is a current work still very preliminary by Mastos and colleagues, as I showed. They found that the rats, which is mutated, have deficits, that's for sure. And now they studied on these rats, on slices, the prefrontal cortex and the pyramidal cells that I illustrated. And they found that on slice, they can show that there is a deficit in the response to acetylcholine taking place on slice. And then they showed that on slice, galantamine reverse the effect of the mutation. And this can also be found preliminary again in the rat itself. So this is for us not only a view that alpha-5 is involved in the function of the prefrontal cortex, but also that one can reverse the deficit of hypofrontality into a more normal behavior. So it's an anti-psychotic drug. And if at the end, I emphasize this cholinergic antipsychotic drug, is that until now, the best known antipsychotic were against the dopamine receptor, the D2 receptor. So classically, the neuroleptics are acting on the dopamine. So this is really for the first time that is being considered as a big discovery in the field for specialists, that a cholinergic agent is acting as a neuroleptic. And this neuroleptic is either an allosteric or an allosteric modulator of the muscarinic acetylcholine receptor. But now we have the hope that there will be not yet nicotinic receptor allosteric modulator, which should become a neuroleptic. Galantamine is an example, but big.
So it's a discipline that I thought you're very if you find it difficult to introduce the same word, you find some finding from the academic point of view, this new concept of Allostery, when we were introducing it for the first time, or it was more.
Was the academic community receptive to the concept of Allostery, or did you find this belief for fighting the community? Did the academic community was receptive to the comment of Allostery?
Well, the interesting thing is I learned that from Martin Karplus autobiography. You can find it. Martin Karplus complained. This was actually in the Curie and Karplus paper of a few years ago, that Allostery has been underestimated by biophysicists for years and decades. And that he was considering that it was a problem to re-investigate using modern technology like molecular dynamics and others. So we